In this recording, I'd like to explain how the input noise is affected by output noise in case like LDO input is voltage difference and output is a controlled linear regulated output voltage. In case PLL, likewise, input clock frequency is referenced to make a higher from 30 megahertz, 40 megahertz to 300 megahertz or sometimes gigahertz. Makes output clock frequency and input clock frequency noise, phase noise, affects output phase noise. So how much output phase noise appears from the input phase noise considered system noise itself generated by parts of the system. For PLL, we have phase frequency detector, low pass filter, and VCO, and feedback divider. Those parts generates phase noise or controlled voltage noise, and in total it's affect the output phase noise is affected by those factors. Especially at first, I'd like to comment on focusing on the phase noise from VCO, like quantum noise, quantization noise in a delta sigma modulator. Because the topology of both are the same, looks same. For delta sigma modulator, we have integrator, two-stage of integrator. Unity gain frequency omega sub u, same topology is cascaded, but in second parts, second order delta sigma modulator has feed forward pass in the second stage, and quantization noise is added in after the second stage, and it makes output, and the feedback is negatively feedback to the input, and quantization noise to output transmission transfer function is noise spectrum, noise signal and noise. This was noise transfer function NTF, and it is in this delta sigma or y equals Qn plus Qn minus y times omega us times k plus omega u over s. So Q, this NTF is written as 1 over 1 plus G of S, where G of S equal just omega sub u over S multiplied by constant K plus omega sub u divided by S. Plus This one. Yeah. And this NTF is K S square K is omega n square omega u square plus S omega u k. This is a function of S which describes the high pass filter, second order. So for quantization noise, the delta sigma system has high pass filter effects on its output. Likewise, PLL, we have PLL, phase noise of input applied to the input, phase frequency detector and charge pump makes the low pass filter, some low pass filter, and it's low pass filter divided by this, and then multiplied by omega VCO, and this is the integrator. And likewise, there's a feed-forward pass for stability, making 0, and in this case, VCO noise, phase noise is applied here after VCO block, and it makes output phase noise. This is feedbacked to the input negatively, and there's a divider 1 over n, n is the integer. For simplicity, where it's okay. In this case, in this simple block diagram, we can generate the transmission from phi sub n VCO to phi sub n out. Likewise, Qn over y, phi n sub out over phi n VCO is written as high pass filter. Just multiplication is sequence is different. This is multiplier, so the function is the same. Just gain, feedback gain is this is 1, but this is not 1. This is 1 for simplicity, and this is 1 over n for simplicity, of course. But in normal cases, these block diagrams are very nominal, and both makes HPF from this to there, from this to there, high pass filter. Let's describe another situation. We have LDO like this one, P-channel pass transistor, and regulation output, and the voltage divider feedback factor. And because of the polarity of this P-channel MOSFET, voltage difference is applied to the negative input of the error amp here, but simplified as VREF applied to minus input, plus input, and negative input is applied feedback signal, shunt signal. This is series shunt feedback topology. And this, if this is the amp is open loop gain is A, the transfer function is A over 1 plus beta A approximately, while A infinity 1 over beta. So we out have some noise if it is according to Wheeler have not some noise and multiplied by 1 over beta. Beta usually less than 1, of course. So this is multiplied some gain and generates output noise. This input noise multiply this gain makes output noise. And if this noise is decreased to be neglected, it's very good for LDO output noise. So we need smallest noise voltage reference here. And likewise, this reference is applied, the logic is applied for this reference clock having phase noise. If phase noise is neglectable enough, very small enough, high pass filter can suppress the phase noise from input because this is high pass filter. High pass filter cutoff frequency going higher, and pass band going to higher, and this suppresses effectively phase noise. Phase noise. This VCO phase noise. While remaining this input noise. Input noise couldn't suppressed by this high pass filter. High pass filter is a function from phase noise of VCO to output phase noise. And so phase noise VCO is suppressed by making cutoff frequency higher, pass band area higher effectively. While we remain the problem with this input phase, but if input phase noise is neglectably very small, we can apply this procedure for the design. Of course, there's a appropriate moderate point of the loop bandwidth because it has some noise. Clock has some noise. Of course, phase detector and this control point also has making some voltage noise from charge pump current. So we need to optimize the loop frequency. But as far as these parts are negligible, for example, these divider and phase detector is made by the logic circuits, and it has power rail noise. So, so that decreasing the power rail noise, we can apply the big decoupling capacitor. And if we have enough decoupling capacitor and very clean signal running through the logic of feedback divider and phase frequency detector, and input clock has the smallest possible jitter phase noise. Then we can apply this logic to make phase noise from VCO negligible. And just a little bit further, look into this topology and talk a little bit in detail. But looking to the wide view, roughly speaking, the system is the same as delta sigma modulator. PLL as a high pass filter for VCO phase noise to output phase noise, like quantization noise to output noise transfer function constitutes a high pass filter for delta sigma modulator. And this is just a story for linear regulator LDO. If possibly we can have noiseless voltage difference, it's the best. And also follows by the PLL cases. And then how? There's a PLL piece of noise in applied from the clock and the PDF, also divider included. For simplicity, negative feedback by divider function, transfer function 1 over S and 1 over N, because the omega angular frequency, omega is multiplied divided by N and makes feedback omega very small. But omega integrated to phase, so that the linearity makes, talking about the phase, we can apply this gain, feedback gain also. It's the same. And this, after this, first of all, there's a function f of s, like charge pump current I sub p over 2 pi times also 1 plus 1 over s c sub 1, like this. This is a large one, this is a small one. Loop filter. And then this is, for example, this f sub f of s is described like this. nominal cases, and this is from into here we have noise or control signal, and followed by the BCO, which has a transfer function of KBCO gain divided by S. Is each integrator. This also integrator like this one, and then here BCO generates a phase noise, P sub n BCO applied, and then makes output phase noise, P sub n out, and feedback. So this is in output to output, and this is control signal noise to output phase. This is finally a BCO phase noise to output phase noise. There are 3 parts of the transmission, and first, talking about P sub n input, and regulating these, just looking into this from here to there. Then in this, cutting here, we have Fk over S transmission, and if feedback factor 1 over n multiplied the negative feedback, the transfer function simply equal this plus this multiplied by 1 over n. And here, if s going to infinity, 0 multiplied by s, fk s plus fk over n, and f is cancelled out, going to fk cancelled out, this is going to 0, and this is n, and if f going to higher, you can see infinity, and this is the finite value divided by infinity makes it going to 0. So this makes low pass filter like gain, this is n, there's some cutoff frequency, pass band finished, and transition band there. And this is first order or second order divided by s, second order, second order maybe, must be. And then next, V sub n CTR to P sub n out. This multiply this feedback negatively. This is added to this feedback factor, and multiply this makes this, which means VNCTR minus NFS F over N Pn out all over multiplied by K over KBCO. KBCO written as K simplified. K over S makes V7 out. So V7 out over V sub C and control equals K over S divided by 1 plus Fk over S. Really? Yeah, okay. At this moment, F is like constant times 1 plus like R plus S 1 over SC. So in this case, F doesn't cancel out. And multiplied S is S K R plus 1 over SC K over N. Then if this is if S going to 0 very small, this is infinity, this is 0, this is 0, this is infinity, this is infinity, so it's going to 0. Also, if S going to infinity, infinity going 0, infinity 0, 0 over 1 makes 0. So this means this is bandpass filter. Of course, there are it's a form of this kind. Numerator has S to S squared, so second order band filter. This makes second order band pass filter. I'm talking about now is control signal noise to output phase noise. Transmission makes band pass filter of second order. Like this one. Maybe like this. This is low pass filter. This makes low pass filter. Second order might be. And then finally we have here to here. This is added, subtracted by this Pn VCO, subtracted Pn out multiplied by Fk over Ns makes P7 out, which means P7 out over P7 VCO is 1 over 1 plus Fk over Ns. F is this, and this is sorry, I misreminded. A band pass filter is S. Why this is band filter? Band pass filter. This is band pass filter, look like band pass filter. This is SC, 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 S square, yeah, S something, not square. This type is band pass filter. I remember this is the first order. And this, on the other hand, written as S square over S square plus something. Some kind of this part. This is high pass filter. Second order high pass filter. Second order. First order high pass filter. Second order high pass filter. Band pass filter. High pass filter. The high pass filter may be like this. This is just one. Because f going to infinity, this may going to 0 and this is going to 1. S going to 0, it's going to infinity. Infinity 0, 0, no, 0. High pass filter. So this is high pass filter. K R plus 1 plus 3 FK NS and this is more S square is multiplied by S multiplied by S multiplied by S S square plus K R F K over N S plus K F K over N C S square divided by this. This is second order high pass filter. So we have this transmission for input phase noise, control voltage noise, band pass filter, a voltage controller, VCO phase noise. If VCO phase noise is like this, it's effectively cancelled out. A stop band. It's in the stop band of the high pass filter of this transmission. But at the same time, we need to this low pass filter cancel out the input phase noise. If input phase noise is like this, we can suppress this stop band. But if the input noise remains larger, it couldn't. It remained like that. So if input phase noise of the clock and or systematic or deterministic noise like from voltage source, power line is very enough suppressed by decoupling, and the divider and phase detector generates small possible phase noise. And like this blue line, it's good with this loop bandwidth of PLL, low pass filter configuration, a high pass filter configuration, band pass filter configuration. But there's a band pass filter configuration there for control noise, and we don't know how much the divider and the frequency detector generates noise. So there's an optimal point for the loop frequency, PLL bandwidth. If input noise is enough small, we can make the loop bandwidth higher, and we can effectively suppress the phase noise from VCO, even if VCO noise there, like this, we can set higher bandwidth like this. And this is effectively suppressed with stop band, while input phase noise is couldn't. So if you have very low noise input clock and digital circuits here in PLL, like the case of LDO having very small possible voltage difference noise, you can easily set the loop bandwidth higher and suppress the VCO noise and very good output quality. But in reality, we have another parts, so we must optimize the loop bandwidth of this PLL. But if we have very good clock like MEMS clock and very good power source supply, best possible one, and very good transistor and very low voltage, possible, we can easily manage to decrease output phase noise, which constitutes jitter.